Hello, this is question 8 from the step 3 paper in 2022, starting with some de Moivre's theorem here. So we need to prove that for any positive integer k is greater than 1, that we've got all of this, and then we need to do the same again for cos. So let's set out de Moivre's theorem then. So we've got a cos k theta plus I sine k theta is equal to cos theta plus I sine theta all to the power of k. So we're going to need to expand that thing out and then compare real and imaginary. I suppose it will give us the two bits. So I'm going to need a lot of width, so I'm going to go down the bottom here then. So expanding this thing out, I'm then I'll write reals at the top and imaginaries at the bottom. I think that's probably going to work out best, because then I can start equating these things afterwards. So for the reals, we're going to start off with a cos to the power of k theta, and then for the imaginaries, we're going to get our first choose number is going to be a k1. Then we're going to have a cos, so we drop 1 power on cos, and we bring in our first sine. So we don't have to worry about any minus signs yet, because we've only had one imaginary term. Then we can go up here. We're now going to have 2 sines, so we will get a minus. We're going to have a k2, and then we're going to have a cos k minus 2. How far have they gone? They've done like 3 terms in these expansions. So this is the second term here. We'll have a sine squared theta. So next time we're on here, we'll have a plus. We're going to get a minus this time on this one. It's going to be a k3, because we've now got a cos k minus 3, and we'll have a, I've left out the theta. It's so easy to get fixated on the powers. I've done it up here as well. I'm fixated on the powers and not write the thetas in. So cos k minus 3, and then I'm going to have a sine cubed, which is why I've got the minus sign. So because 2 of them have made a minus 1 and the other one's left me an I. So I've got that, and then back up here I'm going to have a k4 cos k minus 4, put the theta in, sine to the 4, and then onwards. And then down here I'm going to have a plus again, which is going to be my k5, and then I'm going to have a cos k minus 5 theta, sine to the 5 theta, and then it'll be a minus onwards. Right, okay, close the bracket on that one. So that's the expansion, and now I need to get it to look like that, and it's not far off it, but I've got some sec squareds in there, which is interesting, and they've pulled out some factors. So let's say then, so equating imaginary parts, I can say, so what have we got? I've got that at my sine k theta, which is the thing that I'm after, is going to be equal to, so they've pulled out factors of sine theta and cos k minus 1 theta. So I'm going to end up getting a, well, k1 is just k, so that's fine. Then I've got a k3, oops, 3, nearly drew that as a fraction. And then, right, so they've got sec squared minus 1, which is making me think I'm going to want to have a tan squared, which I've got. I've got sine squared over cos squared. So that works. So sine squared theta over cos squared theta plus k5. So this is going to be sine to the power 4 theta over cos to the power 4 theta onwards. And then, well, I mean, that's it now. I've got tan squareds, and tan squareds are sec squareds minus 1. So yeah, save a bit of screen space, but that is, you can now just write out the answer off of the back of that then. So maybe put in something saying, tan squared theta is equal to sec squared theta minus 1. And then we're good to go just by writing out the answer. So similarly, we can, similarly, it's going to look pretty much the same, isn't it, for real parts. So what we're going to get for the real parts, we've now got cos k theta. So what are we going to pull out here as a factor? We're not going to want to pull out well, we can't pull a sine out. So what do we want to pull out? Just trying to see, what do we want to factorise on this? Have we got really much to factorise? Are we just factorising the cos? That might just be it, but then we've got an extra. If I factorise out the cos k, then I'm in a bit of a mess, am I? Because I'm going to have a... Oh, no, it's working. If I do the cos k, I'm going to get a 1, then I'm going to get a tan squared. So I'm coming out with the same sort of thing. So I'm going to have cos k theta. So that's going to be 1 minus k2. And then I've got a tan squared theta. Find a similar expression. So I want to change that over. And then I'm going to have a plus k4. And that's going to be a tan 4 theta onwards. So, right, if they want a similar expression, then I'll write that out again with sec squareds minus 1, which isn't going to fit on the page. But, you know, you can see where I'm going with this. So I'm just going to replace those tan squareds with these, so it looks like that. Okay, so that was quite a lot to write out for part 1, but going through the motions to a certain extent. Right, part 2 then. So let theta equal cos minus 1 over a, so that's an inverse cos. Then where theta is measured in degrees, right, a is an odd integer greater than 1. Okay, so let's do I want to write out this thing again up the top here? Let's see if I actually need it or not. I might do the previous result that I worked out, but I'll come to that if required. So I've got here that cos theta equals 1 over a, which means I've got a lot of sec theta. So sec theta is equal to a. Okay. Suppose there is a positive integer k such that sine k theta is 0, sine m theta is not equal to 0 for all integers m between 0 and k. Right. So k is the smallest integer for which sine k theta is equal to 0. Show it would be necessary to have k even, and that cos of a half k theta is equal to 0, and then deduce that theta is irrational. Good Lord. Right, so if I've got then, so if sine k theta is equal to 0, then that means I've got all of this thing is equal to 0. Right. So what does that mean? If sine k theta is 0, all of that is 0. So I've got 3 things multiplied together. I've got 3 things multiplied together. So, but sine theta, well, sine theta is not 0 because of that. Therefore, sine theta is not equal to 0 because sine m theta is not equal to 0. Okay, so cos to the k minus 1 of theta. Well, I've got cos theta is 1 over a. A is an odd integer greater than 1. An odd integer greater than 1. So cos theta is always between 0 and 1. So cos theta, so that's not going to be 0 either. So cos k to the minus 1 theta, because k is greater than 1. So yeah, that's not equal to 0 because cos theta, well, it's essentially, I'm saying, because why does it matter that a is odd? What's that got to do with anything? I mean, maybe that comes up later on. But the fact that, I mean, if a was even, an even integer greater than 1, then not quite seeing the relevance of a having to be odd at the moment. I mean, it feels as though maybe this is anyway, 1 over a is not equal to 0. Therefore, cos theta is not equal to 0. So that's okay. And then, I mean, if nothing comes up about this odd, I might have to come back and think about that again, because I don't know why they put that in at the moment. Anyway, so I've got that. So that's not 0, that's not 0. So it'd have to be the bracket that would be 0. So if the bracket is 0, then so bracket must equal 0. So how are we going to get that to be equal to 0? We've got, maybe this is why it matters that a is odd, because we've got sec squared minus 1. So if, no, so as is not if, so as a is odd, I've got sec squared theta minus 1 is even. Oh, well, yeah, so that's probably going to be of more importance than before. So what is, and k is, oh dearie me. So I need to show that k has to be even. So the bracket then, well, this is even, that is even. Okay, right, so each term, I can see where this is going now. Each term in the bracket is a multiple of sec squared theta minus 1, except, put that in brackets, first term, which is k. So therefore, if bracket equals 0, k must be even, else we have an odd, well, I mean, you can say plus or minus an even, plus an even, minus an even, etc. So if we're going to get 0, then k has got to be even. Right, okay, so that's dropped out. So k is even. What does that mean? So if k is even, so if k is even, which it must be, and of course we're still working on this idea that sine of k theta is 0, then what does that mean? So they're saying that it's now necessary to have cos of a half k theta is equal to 0. So we're going to want to split this. I mean, suggest we're doing double angle on this. So sine k theta is going to be 2 lots of sine k theta over 2 cos k theta over 2. Okay, and we want that to be equal to 0. So we're saying then that sine k theta over 2, we need a justification for that not being equal to 0. So I'll put down what we inevitably need. So sine k theta cannot be equal to 0. And why is that? Why is that? K is even. So that is a, well, that's our M case. That's our M case. Where, yeah, okay, so because k over 2 is an integer and it's less than k, and we've got that sine of m theta is not equal to 0. Okay, so we've got, therefore, we've got that cos k theta over 2 is equal to 0. Right, now we have to deduce, good lord, it goes on forever, this bit, doesn't it? We have to deduce that theta is irrational. Right, okay. So we're saying, what are we saying? We're saying there's no, God, what have I said here? So I've said that, so k has to be even in order to get sine k theta equal to be 0, but then we've got cos k theta over 2 is equal to 0. So does that mean I have to go back and look at cos? I don't see that there's a quick jump here of saying, well, so we've got some integer number of theta goes to sine goes to 0. So that's going to be a multiple of pi. Oh, except we're measuring all this in degrees. So yeah, I can't see a quick jump of just saying, yeah, this is now going to drop out at last. But do I have to go into cos? Do I have to go into this bit? What did I work out for what cos was? So it's all of this thing here. So if I was doing, maybe I'll just want to copy this across. Well, let's work out here. So I want to say here, if I've got cos k theta over 2, let's do this part, get back on the right sheet. So cos k theta over 2, essentially I'm doing the same thing as I've just done on the previous part. Let's see if this helps. So I've got k over 2 theta, and then I've got 1 minus k2. Well, I don't really want to have tan squared, do I? If I go back to the sec squared, so I've got the same issue. I've got the same thing here because I've got an odd. These things are all going to be even. So this is odd. And then I've got minus even because they've still got these same factors. They've still got the sec squared theta minus 1 in them. So I've got odd minus even plus even minus even. So this is not equal to 0. And then I've got cos to the k over 2 of theta. And this thing is equal to 1 over a to the k over 2, which is also not equal to 0. There's just no answer to this then. So, right, so I've now shown that that doesn't work either then. So we've got, well, it doesn't work for integer values. It doesn't work for integer k. So, right, just need to, I feel as though I've almost got this now. So there's no, I just can't get the last bit. So what am I saying? There is no k for this work, for that makes this work. There is no, there is no, so this is another one that is not true. As shown on the previous sheet, obviously you'd put it sequentially in your actual answer. So there is no integer, what is positive integer k, positive integer k, for which sine k theta equals 0. Right, so what does that mean? So if I've got sine k theta is equal to 0, then that means I've got, so i.e. k theta does not equal n times 180. So theta does not equal n times 180 over k, so it's irrational, right? Because that's just a ratio of integers. Right, so good lord. Right, that was a lot to deal with. Again, they seem to be requiring a lot of writing in the questions in this paper. Certainly, I mean, question 6 was another one. I just couldn't fit it all on the screen. I've got the same issue going on here. Right, let's try doing the last part then. Anyway, see if that fits on. Show that if phi is cot inverse cot of 1 over b, b is an even integer greater than 1. B is an even integer, A is an odd integer we had there, so we flipped over, then phi is irrational. So it's got a lot of similarities with what we've just done then, so it feels as though we've got similar techniques that we can use with all of this. So, right, so if I've got that, well, what am I doing? Well, I'm saying that I don't need an if. So cot phi is 1 over b. So tan phi is b. And I can rewrite all of these with tans in. So what is that going to mean? So I need to do this essentially the same thing. So let's try. So how did they put it? Suppose there is, I'm just copying out this because this is what they've done. A positive integer k such that sine k phi equals 0 and sine m phi does not equal 0 for all integers m with m between 0 and k. So we're just starting exactly the same way that I had before. Now I can do my sine k phi, and I can put it into this thing with tan squareds in instead. So that is going to be sine phi cos k minus 1 phi k minus k3 tan squared theta plus k5 tan to the 4. So this is why they've changed the b to be even, because then this is now, yeah, so I need to do that. Yeah, this is showing that k must be even for the same reason. So we're going to have that sine phi can't be equal to 0 because of this condition. So that is not equal to 0 because sine m phi is not equal to 0. What am I doing with cos? Okay. Cos k minus 1 of phi. So cos k minus 1 of phi. Oh, well, if cot phi is 1 over b, then that is not equal to 0 because cot phi equals 1 over b, and b is an even integer greater than 1, so that's fine. So we've got not 0, not 0. So the bracket must be even in order to get a 0. So else we'd have an odd minus even, even, even. Must be even because tan squared, I've written thetas on these, phi's. Tan squared phi is even. Okay, right, so that's shown once again that we must have even k, otherwise we can't get anywhere. So if sine k phi equals 0 and k is even, then we can go into the cos one. So we're going to do the same. This is identical to the previous part of the question. So we've got cos k phi over 2 is what we were going for on this. So we've got exactly the same setup as we had before. It just feels like I'm repeating everything I've written. I'll just write all of this again. So all of this stuff you can put in again and say, okay, well, we can't have sine k phi over 2 being equal to 0 because of the m condition. So that's all identical. So it's got to be cos k phi over 2 is equal to 0. And then we can say, well, actually, haha, no, it can't be, because we're going to have the same setup. We're going to have a cos k over 2 phi. And then what was it? It was a 1. And then minus k2 tan squared phi, and then plus k4 tan squared phi, so dot 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 dot. So therefore this cannot be equal to 0, which cannot equal 0. So because the bracket is odd minus even plus even minus even, etc. So therefore no value of k for which sine k phi equals 0. Therefore k phi does not equal n times 180, phi does not equal n times 180 over k, therefore it is irrational. Now that was a weird end, that third part of the question, because it is pretty much an exact duplication of part 2. So it seems to me that anyone who does this question will probably do quite well on the first part, and then if they do part 2, they'll also get all the marks for part 3 because they're doing exactly the same thing again. Or if they don't do part 2, well, they ain't going to do part 3 then. So that's a weird setup of a question, to just essentially give double marks to a part of a question. So it's sort of all or nothing, this one, really, isn't it? But still, that's ended the pure section for this paper.